Good day, everyone. Welcome to a very exciting webcast for Golden Helix. I'm Cheryl Rogers, the Director of Marketing, and today we officially announce our newest software solution, VSWarehouse. I have here with me Dr. Andreas Scheer, our CEO and President, as well as Gabe Rudy, our VP of Product and Engineering. And before Gabe gives us a glimpse into VSWarehouse and its applications, Andreas Scheer will introduce VSWarehouse, our reasoning behind the product, and our vision. Andreas, the mic is yours.
Thank you, Cheryl, for this very nice introduction. Good morning, ladies and gentlemen. So it's a beautiful outside here in Montana, sunny skies and fantastic ski conditions. And inside of the offices, everybody is very excited about today. We are unveiling for the first time a product that we actually have worked on for quite some time, a data warehouse solution for data. And we will spend a good hour or so today talking about what we have here in the store for you. Now we have a lot of people on this call from across the globe, and a lot of them have been with us for the first time. So please allow me to talk a little bit about Golden Helix so that you know who we are and who you're potentially doing business with. So we are for almost 18 years now in business, founded in 1998, and one of our largest stakeholders, external stakeholders, GlaxoSmithKline, is with us from the very beginning. In terms of our offering, we have really two product areas. There is the VarSeq suite, which is clinically focused. In its essence, it's a filtering annotation platform. It allows clinicians to create clinical reports modeled off the ACMG guidelines. For our high throughput clients, we have the ability to run all the workflows in a pipeline, which is much more performant and allows for high throughput. And then as of today, we have a data warehousing solution to offer. On the research side, we have a product called the SNP and Variation Suite, and that product is very powerful and allows for a number of research workflows, so you can conduct genome-wide association studies with this product. We are supporting genomic prediction. We can do large N population studies and many other research-oriented workflows. In terms of our customers and who do we business with, so we are in business with now over 350 client organizations globally, and they really fall into 5 different brackets. So there are the large hospitals that buy from us. Then we work with major research organizations. Here you see Stanford, UCLA, but many, many others. Then there is a set of clients that fall in the testing lab category, so prevention genetics, for instance, or some of the NCI centers, and many more. I already talked about GlaxoSmithKline, but really we have a number of the major pharmaceutical companies who buy from us, so Bayer, Eli Lilly, AbbVie, Teva, and many more. And then last but not least, the 5th bracket is basically the government organizations, and here in the US it's the NIH, NCI, USDA, and other agencies. So within those 350 organizations, we are approaching about 10,000 actual users. So it's a significant customer base that we have accumulated. Our clients use our software to get published, so we're now in over 950 peer-reviewed publications mentioned. Among those is Science, Nature, and Nature Genetics. Actually, we think that we're going to break the 1,000 citation barrier in about a couple of months or so. So why does it all matter? Well, first of all, whenever we come out with a new product like today or a new release, it's really not a brand new technology stack. A lot of the components that we are using, for instance, for VSWarehouse, actually have been used and tested in the SNP and variation suite and VarSeq for many, many years. So it's a tested and proven technology stack that we bring. And whenever we launch something like this, or just a new release, or a new annotation track, or simply documentation about it, is being immediately scrutinized. So there is a network effect that new clients actually benefit from, because it's the little things that are making the life simple or can actually create problems. And this huge customer base allows us to get the little things right. We are deeply ingrained in the community, so we participate in conferences, we speak, we sponsor events. You'll find a lot of content on our website on webinars like this where we share best practices, or there's a series of ebooks now that talks about some of the industry topics, like here in this example, genetic testing for cancer, and many, many more. In terms of our business model, and this is very important, a lot of our competitors have chosen to adopt a per sample pricing. We don't subscribe to that. We actually have a very, very simple way to do business with us. We have a subscription model, an annual subscription. Everything else you need, like training and support, comes with it, and we really want to make sure that our customers maximize their use, leverage our technology as much as possible. And then last but not least, and that's mostly important for our research clients, is there's a lot of transparency about how we implement things. So you can review our methods. There's the math is revealed, citations, and other things. So it's possible to externally vet the methods that we have embedded in our product. So let's talk about the topic of today. So what drives us to launch a data warehouse, and what's the reasoning behind it? Well, there is a lot of it is motivated by the success of precision medicine and the anticipated future growth in this segment. So there's an interesting study from the Grandview Market Research Organization, and they estimated the whole exome genome market in 2014 to be about in the $2 billion range, and they anticipate about a 40% annual growth throughout the year 2022. Yeah, mainly driven by advances in prenatal testing and oncology, but there's also other areas that drive this. And what does that mean for the individual lab? Now, well, it means a lot of data, because if you look at it from a sample perspective, so depending on how much data you retain, a sample footprint is, probably minimally 200 megabyte, but really, if you retain the artifacts of the secondary pipeline, BAM files, and all the context information about the filtering and annotation process, as well as the VCF file, you can easily have a 200 gigabyte footprint and more. Now, the smaller labs, so what I can say from our experience, they have maybe a dozen or so samples per month. The larger ones are in the 3 digits or hundreds of samples, and if you look at the annual output of a lab, there you're very, very quickly looking at billions of variants, assuming that a whole exome or whole genome basically creates 3 billion variants per. So you're talking about billions of variants and terabytes of data, and terabytes meaning measured in 2 and 3 digits, and potentially going beyond that very soon. On top of that, there is a 40% annual growth, so that means in 2 years, the lab will look at twice of the data volume that they're processing this year. So what does a genetic data warehouse look like? And here's maybe just a high-level picture of how this all works. So there is, on the upper corner, you see the bioinformatics pipeline, secondary analysis, alignment and variant calling, then there is the tertiary analysis, and then ultimately the clinical reporting. All these steps create data that needs to be captured and included into the warehouse. Then we have external databases that clinicians use as a reference point. ClinVar is an example, Cosmic, many, many more. And the clinical warehouse basically has a unified data model that allows us to get visibility on all these data elements in one single spot. And from there, we can derive then reports. We can create custom queries, and we can use this database as a annotation source that feeds back into the bioinformatics pipeline. So that's on a functional level what's going on. And of course, we like to see the clinical data warehouse and also being the logical integration point between the lab and other applications and systems within the hospital, or as a way to share data with other labs and collaborators. So some of the use cases that we have in mind and we found now in discussions with our clients as most helpful and important are the following. So and the first one I kind of touched on already. So we want to use the warehouse as an immediate annotation source. We want to create a knowledge base that whenever we have already processed a sample and we came to a clinical diagnosis, we want to use this as a data point going forward. So whenever I sequence a sample, I want to be able to say, have I seen this variant before in my own clinical practice? It's also important to understand, have I seen, at what frequency I have seen this variant? Yeah? This is very important for those who are specializing in particular minority populations or in particular disease categories. Then on the warehouse level, we want to be able to answer clinical questions such as, has the classification of a variant changed, right? So is there a variant that has been classified as of unknown significance and all of a sudden there is a new paper popping up and it's all of a sudden clear that there is this variant is pathogenic? Issues like this can very likely trigger then clinical actions, follow-up activities that are important to track. On the research side, the data warehouse would be a great way to extract data from affected and unaffected study participants so that you can conduct future research. And in fact, you can use one of our products, the SNP and variation suite, to do, for instance, a case cohort analysis. And then lastly, it's the aspect that I touched on early on. We need to have a structured way to connect with other legacy systems, and a warehouse would be the perfect integration point for that. So much from me as an introduction on the subject. If we will spend the rest of this webinar introducing you to VarSeq Warehouse and some of the architectural choices that we have made to solve this problem. If you have any questions, feel free to type those into the question pane on your screen, and then we're going to review at the end of the call and see, depending on how much time we have, we'll go through this. So with that, it's my distinct pleasure to introduce you to Gabe, who is VP of Product and Engineering here at Golden Helix.
All right, thank you very much, Andreas. So to get started, as Andreas said, we're building off of our existing product suite and our existing track record providing clinical annotation, filtering, and interpretation workflows for labs that are doing genetic tests. And I'm going to basically need to set that context up a little bit as a motivation here. I'm not going to be able to go into the details of how these workflows are constructed and what our solutions are. We have great webcasts, and I think there's one that's called Using VarSeq for Clinical NGS NGS testing if you wanted to get into more of how all these components works, but I do want to basically set the groundwork here, and for those who aren't familiar, be able to at least give you a frame of mind of what that solution is. And this is all in the context of the life cycle of launching and successfully supporting NGS test in a clinical environment. A lot of that life cycle we've talked about in the past is all about this work of setting up your R&D to essentially define what is unique about your test. This means taking the data coming off of that secondary pipeline that Andreas mentioned that calls your variants and often puts it in a VCF file, and adding the annotation sources that are going to be helpful in doing some bulk filtering as well as helping the interpretation process. This often includes ClinVar, which is our NCBI's catalog of clinically relevant variants and how they impact human diseases. And very importantly, things like annotating against genes and knowing how a mutation affects the transcripts that transcribe to protein sequences and whether it modifies those and which transcripts and what type of effect it has and how you describe that variant using clinical terms like HGVS, and adding things like population frequencies, just knowing how often does this mutation occur in a healthy population at large. Of course, this is a very dramatic simplification. Each one of these sources contains dozens of actual individual fields, and there's lots of different options for most of these choices, but this is essentially the bulk or the process of setting up a test, is choosing these parameters. We give you a lot of starting points, but ultimately we allow you to make this very specific and optimized for the tuned of the sensitivity and specificity you need. And then ultimately the interpretation step involves having that very important human aspect of having a trained professional take these candidate variants that might come out of your tertiary annotating and filtering process and evaluate them in the context of an individual's patient and their phenotype, referring information, etc., and enter that all into a structured form. And this is our report system. So our report system allows you to find the fields that you're capturing about a patient, allow you to define which variants you select. Here we select 2 pathogenic, 1 incidental. And then with those variants, you can provide individual classifications of those variants. All this is going to be important as we talk today because we store this information right now locally in your VarSeq instance. We store it in a structured form. We could also render it into beautiful reports. But as you launch your test and over time, the idea is to really be able to take advantage of the hard-won treasure trove of data that you have by having clinically screened and highly accurate variants calls generated. You want to start to catalog this information, not just the information about these bulk variant matrices and all the calls, but also the structured information that you laboriously captured and put into these reports, as well as why not have the reports themselves be something you can retrieve at any time. So over time, you want to catalog that. You're going to be able to do things like go back and do data science on that catalog, pull out predictive trends or even just simple association trends, or look for highly mutated genes within your cohort, or more specifically, being able to have a feedback loop that tunes your sensitivity and specificity for the next round of your update. You may update to a new set of technology, a new set of annotations, and you want to be able to retrospectively do that type of work. Finally, the world of annotations like ClinVar, these population frequencies are changing over time. You need some way to take all of the data you've previously looked at in, say, last year's world and look at it in this year's context of all the public sources we have. And finally, you also want to think about, do I have a proper medical archiving system where I can go back if someone asked me and said, oh, why did you assess this variant as pathogenic? Well, here's the data I had at the time. Here's the information about all of the samples I'd previously seen and their frequencies. Here's what ClinVar said at the time. Here's the population frequency catalog we had at the time, and this is the assessment I made. So having that snapshot to be able to preserve exactly what you have and being able to pull out the raw data in its original form in its entirety really makes sense to be able to support clinical testing in the long run. And hopefully we can all do this in a way that doesn't require massive support teams and a lot of specialists and a lot of hand coding, but in an integrated way that anybody who is able to understand what they're doing on the genomics side can design a system that works for them. So that's the idea of, that really motivates this concept of building a warehousing solution, because that's what warehousing solutions are, is a place to put data optimized for queries and long-term storage and access from a number of different systems. And what we're talking about is a variant warehousing. And really, if you think about what's in a VCF, it's not just about, say, this sample has this genotype. There's all this call information, a lot of supporting information, quite a bit of information there, and we don't want to throw that away. I mentioned that because as we really scale these systems, a lot of other solutions do compromise and throw away a lot of information in the VCF purely out of necessity because they can't scale otherwise. If we store everything that we got from our upstream pipeline, we can ask at any time in the future, was there some extra piece of information that we could tweak or tune and put into our filters to help improve our sensitivity going forward if we missed something? Or, oh wait, why did we miss this variant? Well, we had a filter that wasn't tuned. What if we had this extra parameter in there from our VCF files that we're totally ignoring? Oh, that really helps us, right? Also, we want to be able to, over time, pull out the original files that we inputted, so a single sample and all their variants, as well as, more likely, pull out subsets. You might do a cohort analysis of cases and controls. You might look at a single gene and pull out all the details for the variants in that gene. You might want to be able to just take this and share it with a friend and export some data, or have a colleague that you have a research relationship with. So these are the types of questions that we end up asking of a variant warehouse. Andreas mentioned some of these, being able to just see which samples has it been in before, at what frequency, and also critically, what was the actual genotype information? How many times have I seen this in a heterozygous state where just one chromosome had a mutant allele versus both chromosomes having a mutant allele for this mutation? Also, you're going to see a lot of variants that are completely novel in your clinical samples. That's the beauty of next generation sequencing. You see what's there even if it's never been seen in the world before, but that doesn't mean that the work you've put into building previous assessments and interpretations might not come in handy. You simply just need to expand your look into a genomic, into the neighborhood of where you are in the genome. So expand that out to look at the current exon or the current gene. Maybe you have a variant in your warehouse from a clinical report that you've in there saying that this variant is pathogenic and it's just 4 bases away from the one you're looking at. You can probably share a lot of the interpretation of what mutations in that gene means in terms of clinical impact. And finally, you might also want to simply keep track of things that are changing. As Andreas mentioned, ClinVar releases new variants that have clinical assertions every month and also change previous assertions, and you want to be able to get alerts on that kind of information. So over time, this type of information is being added to the warehouse, being extracted, but you don't want to just think of your warehouse as just this current snap point of the most recent annotations and the most recent matrix of samples and their variant calls, but ideally, you'd be able to go back and see what the world looked like a year ago. As I mentioned, that's very helpful in different contexts. So what is it that we're storing, and what's the scale of the data problem here? So allow me to orient you to essentially what happens when you merge a bunch of variants from VCF files. And in this dimension here, we have in our rows of these tables here would be our variants. And what we're storing ultimately is the total number of unique variants across all of our samples. So we have a bunch of identifying information about where that variant is, etc. And then we have a bunch of information that's just purely at the variant level about our annotations from these population catalogs, gene annotations, ClinVar, etc. Of course, these can change over time. And while this may just one column or a couple columns, keep in mind that these catalogs have quite a bit of information. We don't compromise and reduce that, so you may actually, very commonly with a project, have about 260 columns of annotations, which you probably are only looking at a couple at a time, but when you really drill down into a given mutation, all of those columns are going to be helpful for interpretation. So there's hundreds and hundreds of annotation columns, and then for a given sample, when a variant is called by an algorithm, you're going to get the information of the genotype, how many chromosomes had a mutated allele, but you also get quality information about the read depth at the time, the number of individual NGS reads that support that mutated allele versus the reference allele, etc. all this information you can think of a table, but it's a table that has the dimensions of for every unique variant. We have information for this sample, and then we have the same amount of information for the next sample and the next sample and the next sample. Where all of our samples, we would have some information about, their lab information, their infection status, etc., on another table. So what this means is this call field these call field tables end up becoming the largest dimension, and the number of rows in here is really the number of samples by the number of unique variants in your system. So just benchmarking this with some exomes, and some of the projects you see today will actually be in the scale. 10 exomes, it's going to be common to have about 500,000 unique variants. So now you're looking at 500,000 rows. But soon, very quickly, you get to 100 exomes, that's about 500 million rows. And then you get to 1,000 exomes and 12 million unique variants. You're in the 12 billion rows. And so technologically, if you're going to build this yourself, your first instinct might just to throw this into one of these, very mature relational database management systems, RDBMSs, MySQL, Postgres, even Oracle. These are all built along the concept of having an online live system that you can insert, update, and delete rows. And they certainly do scale to billions of rows, and you can throw a 12 billion row table together. But it turns out it has very, very poor performance for these types of queries. When we're going to query a warehouse, we're going to look at just one attribute, one column, and say, or maybe 5 columns, but you're still going to ask things like, show me variants that are rare, that are in ClinVar, that have a sample read depth of 20, and making those types of queries across these row stores ends up scanning every single field. And remember, we have hundreds and hundreds of fields of annotations for all these billions of rows, and it takes tens of seconds, sometimes minutes. I had one table actually that I was playing with that had 20 billion rows in it. Take 2 hours to do a simple query on it. And so to try to optimize that, you start to put the data into very unintuitive star topologies where you place your annotations from ClinVar in one table and your variants in another and your this and that, and all of a sudden you have to join 15 different tables to make any sense of it, and that's very cumbersome as well. But one thing these systems do build over time, and it's become a very popular way to extract data for any purpose, is having an SQL query language where you can, with a very powerful high-level language, extract very specific queries to get to the underlying data set. So that's nice, but the storage and speed requirements scales very, very poorly. So let's look at another thing I've seen people try to do with genomic data, and that's store it in NoSQL formats, where you say, here's a variant, and that's the key, and then I'll stick everything I know about that variant into its value. Well, you can definitely scale this. Again, it's not very space efficient, but it has a very, very poor query interface. You essentially have to create another index on any dimension that you're going to actually query the data, because inherently it's not tabular. And we have an example of just storing without the variant calls on the order of 1 million variants takes about 20 gigabytes of MongoDB, and then you're only querying, in this case, on the gene level and not being able to do anything more advanced than that. So the approach we take is the one that enterprise data warehouse solutions have taken for at least the last couple years, and it's definitely to the point where any solution not based on these read-optimized matrices is falling behind in this space. So we're building a genomic-aware, read-optimized, batch-updated data warehouse. Batch updates means we don't have to insert rows and delete rows. What we're going to do is add bulk samples. We're going to add 1 million variants at a time. We're going to add, dozens of samples at a time, or even one sample at a time. We can recompute what really is a recomputation, this unique set of variants by samples. And this can scale very well, both in disk and query speed, because we can optimize the read usage of going down and looking at a single column at a time. And we can have a very intuitive topology. In fact, if you were to look at, and we can actually still have an SQL front end, and I'll talk about how we do that in a second. But if you were to look at our SQL table, it looks like a table with hundreds of annotation columns, but as you query individual columns, you're not scanning that entire table. You're optimizing the query to go and look at a single column, pull out those rows, and then you can pull out the rest of the data you want for those rows. So this is one of my favorite quotes from Michael Stonebreaker. Probably, if anyone could be called the god of databases, he would be. He invented Postgres, launched 2 or 3 commercial database companies, including enterprise-based warehousing solutions that he sold off to HP. And in the case of data warehousing workflows, his take is that traditional row-based data storage is a completely dead approach. And a column-based storage system will have a performance factor of 100x, and that's probably a bit on the optimistic side, as any good quotes are. But actually, so going into my next slide, I pulled a little benchmark of a simple exome project with 10 samples, and threw that exact same matrix of data into a Postgres database, and that 10 sample 500,000 variant table took up 2.5 gigabytes, and just doing a query on a couple of annotations and a sample attribute took almost 10 seconds. That same information in Warehouse takes 16x less speed and 11 times faster in terms of query performance. I didn't have time to put a table in for a larger use case, but the exome project we'll show later today that contains a set of fully normalized GVCF research exomes. We put 100 exomes together there, and that, if you were to translate that directly to a Postgres database or really any of these row stores, that took about 220 gigabytes of storage, and in VarSeq only took 5 gigabytes. So that's a 40x improvement in speed. So actually, as you scale, you might get to 100x, and certainly because we're able to take advantage of compression along these column stores, as well as having very, very efficient indexing and genomic aware indexing. I'm not going to get too much more into the technology about how we store this data, but it is important to note that this is not a new technology we're inventing just for VSWarehouse. This is in fact a problem we've been solving for genomic data for a long time, and I actually wrote a blog post as I introduced this column storage system that we use for our annotations and our project information in VarSeq. So you feel free to go and look that up. It's called TSF, etc. But this is essentially the core technology behind VSWarehouse, and it scales to thousands of exomes, thousands of genomes, and very efficient in the storage space. And it makes for this very easy querying where you can have all the underlying logic that we are having to do to, say, join to different annotation sources and make one-to-many joins and all that is completely abstracted away. And the way we present it in Warehouse, it looks like a single SQL table. It's very slick. The other problem we're solving is not just the storage problem, but the genomic problem. So you may go and find some storage solution that does match these requirements, but good luck trying to get your hundreds of VCF files from different vendors to all normalize into a single matrix. It's a very difficult problem, and one we've been solving since VCF files have been invented and over time. So VarSeq's core technology stack here is being used to handle things like merging variants, left shifting, normalizing allelic to primitives, bringing all this into a single matrix and allowing that to be in an efficient format. We're also adding our own annotations on top of that. We do our own gene annotation algorithm, which breaks everything down by transcript data and rolls it up to gene level impacts and combined and clinical transcript oriented forms. We describe variants in HGVS. We keep a very extensive public catalog of annotations going. We keep that current, and we allow you to update at your own speed when you want to pull in the latest annotations. We also have a number of licensed annotations from commercial vendors or private institutions you can access and bring in real time. You can also curate your own annotations, and we have wonderful GUI wizards for doing that and can convert any file format that has genomic information. We have QC algorithms for QC on the sample level, at the variant level, coverage statistics, cohort algorithms, basically anything you can imagine that you're going to need to slice and dice your genomic data is at your disposal to be able to leverage when constructing your warehouse. And all that comes from the VarSeq technology stack that we've matured over the years. And finally, the integration here is as easy to use as using VarSeq, because VarSeq is the core driver of putting data into the warehouse. So all the interpretation and visualization you're used to in VarSeq is able to essentially just be augmented by having a server which contains all this data collected over time, and that server can be used both to pull in information to help your analysis, things like your population frequencies, and it's as easy as just saying, add my samples to the warehouse server, and it puts them up there and puts them in a batch queue to be processed. So all this information can be accessed within the comfort and within the efficient workflow that you've already set up for handling VarSeq data. Okay, so let me break down one final slide where I talk about what we're storing inside of the warehouse, how VarSeq interacts with it to put data in and out of these different components, and how you can interact with it outside of VarSeq, both through a web interface and through an API access. So first, what we're storing is these big matrices that we just talked about. So this is the variant store. These are the actual sample calls, the variant calls, without throwing out a single piece of data, every piece of information from your VCF files normalized into these projects. And one thing, like I mentioned, it's nice to be able to go back in time. We do is every time you add samples, you actually get a new version. So here's a version 1 that had 50 samples by 5 million variants. You add another 50 samples, you get a version 2. You can look at any time. You might add a new version that updates an annotation, et cetera, et cetera. All these are completely self-contained. Essentially, what you're seeing here is these projects are efficient folders full of our TSF files, and then all of those are bound through a database abstraction layer to have a SQL query interface that allows them to look like simple tables that can be used from a web interface or from an API system. And then to upload your data to that, it's as simple as opening up your VarSeq project, going to your warehouse manager and saying, update this project with my samples. And you can also create a different warehouse, and you might do this just to keep, say, your clinical samples separate from your research samples or your tumor samples, which have somatic mutations, and you don't want those mutation frequencies integrated with your hereditary samples, for example. The second component we're storing is everything that we're capturing in our structured report information. So as you select a variant in VarSeq to put in a report, you're going to say this is pathogenic and this is not, and then you can place that in. You can, without having to leave VarSeq, you essentially render that and you get a version of the report on the server as well as it being indexed. Also, for all of our exome, or for all of our projects, we're creating these frequency tables, and these frequency information can be visualized as well as put into your automated workflows to help your filtering. And finally, you can set up custom, very customized fields to be able to capture information about variants such as, is this variant a false positive, or maybe you have a collaboration with another lab and you can integrate their data stores as well. All this can be queried. Each one of these can be queried as a view that can be filtered by any of its attributes using the Harvest biomedical toolkit that is an open source technology from CHOP. And our query interface itself is open source, so you can extend that to your heart's content or use it as an example of how to access this data from an API perspective. And also, as I mentioned, the query interface from a SQL or a higher level interface is very intuitive. Okay, so with just maybe about 10 minutes to go, I'd like to touch on demonstrating what this looks like from the perspective of someone who might go into a report and want to leverage Warehouse to aid their process of writing a clinical report for a tumor sample. And then we'll go in and query the Warehouse to see those variants that we just put into the Warehouse, and then we'll come back and look at this from the perspective of diagnosing an exome trio, where you have a child, mother, a father trio, and you're looking at a different context and authoring a different style of report. So with that, I'm going to come back to the web interface in a second and go ahead and launch VarSeq. And I'm sorry I'm not going to have time to introduce you much to VarSeq, but I am going to just give you a sense of what the standard, so this is essentially what one has when one uses VarSeq as a workflow engine. You can open up a project, and this project can be constructed by our pipeline tool to have all of these annotations in your project and your filters already defined. In this case, we have 3 samples, and we're filtering 100,000 variants down to 15 or 115 variants. We have a set of visualizations to help interpret those variants. We can look at which variants are where and where they are in the gene, what their coverage is, etc. And let's talk about how we work with Warehouse from here. So I'm going to go to Tools, Manage Warehouse, and this brings up a list of all my projects here. I have my URL for warehouse.goldenhelix.com. This is our cloud-based server that we're using for beta testing, but you would have your own internal URL. It does not need to be on the cloud. It can be on a local server. We have a couple projects here that we are working with. We also have a number of annotation sources, a number of reports, and we can go ahead and open up one of these reports and open up in VarSeq to be able to capture the information about the sample, its referring information, as well as information about the variants that we might be interested in. So these sections here are primary findings or secondary findings. These are configured from our table, and as we select a variant of interest, a candidate variant here, it gets added to our list of findings, and I can remove it, and then we can adjust its pathogenicity, classification, and write notes about it, etc. So all this allows you to capture information about the sample, about the individual variants that you've put in there, have a secondary findings, and when we hit this button to essentially render the report, we get sent to a URL on the Warehouse server. And of course, we need to log in because this is internally an authorized access to the server. Otherwise, it's important to keep in mind that you can have at any time your information, your authentication is going to be automatic, so you can see your variants is going to be using your authentication that's already in VS, that's already in VarSeq, and so you can go ahead and view these reports. Go ahead and try that one more time. Looks like I have a different version of my sample here. So I'm not going to be able to view the reports today. We're in active development here. And we're going to also jump on out and save the reports as PDF, and we're going to go ahead and look at what these reports look like when you're actually in the server. So I'm going to go ahead and visualize the table that contains all of my previously reported variants, and this captures all of that information that I have just entered. So this includes the variant I just saw here, the TET2 variant that's likely pathogenic, and I might want to, for example, go see, is this variant in my other warehouse projects. So in my standard warehouse dashboard here, let me orient you, you can see all the variants you've had over time. You can see all the samples you've had over time as you've added samples, and you can see how much space that's all taking. In our case, we have a set of clinical exomes, research exomes, and our tumor panels. And we can go look at, and we actually have from here a couple of different versions, and we can go say, is this sample that we might want to go look, for example, to go find the rare variant that we just saw. And to do that, I can filter on any number of the annotations that we added to our warehouse project. So this includes things like, let's look for our loss of function and missense variants. And there's 3,000 of those, and we might want to also look for rare variants. So we will use the exact catalog here. And there's 0.01 there, so that's a less than 1% or missing in the exact catalog. And we might also even want to do things like look at functional prediction scores. So these are scores from tools like SIFT, Polyphen, etc. And we can say, let's look at any variants that are predicted by at least half of those algorithms as being pathogenic. So now we have some rare, interesting functional mutations, and do we also have that variant that I just copied and pasted from my previous report? Is that in this warehouse? And I can search for an individual position. And that variant is not in here, but if I remove any of these other filters, is it in here? No, it's not. In fact, there's no variant in here with that set of coordinates. So that's because this is the version of the warehouse that didn't have that sample uploaded. If I go back to my project list, I actually had two versions here, and that second one actually included those samples uploaded. And if I go and query for that position here, I should be able to find it. And there it is. There's the one variant from the warehouse that contains that. And if I go and look at the results, I can find that variant where it is in the gene and the full details of the annotations, etc., that we have already had created here. So that's just to give you a context. At any time, I can also customize the visibility of which fields from my full set of annotations I'm looking at. I can export this information to an Excel file. I can also export it with sample coordinates to a VCF file, etc. And so that's going through and doing this with a tumor sample. And let's go ahead and also, I'm going to close out of this guy and open up a project I already have open. Sorry for the context switch, but this is a completely different project. And this project contains a more advanced workflow oriented around trios. So here I have 3 samples for a single trio with 50,000 variants. And I have a number of different bioinformatic filters set up to look at different inheritance models. Here's my de novo candidates, here's my compound heterozygous candidates, etc. Each one of these I might spend time investigating. I have a table here that allows me to look at the information about those call sites for the daughter and the mother and the father. There's a number of useful annotations already applied. And if I click on any of these given filters, I can drill down and look at just this sample's information. And again, I might be wanting to interpret this individual variant that is in SMAD4 because it looks like a interesting, rare, and completely novel, and it's not in any of the, let's see, is it in exact, for example? It's not, sorry, that's the gene annotation. Is it in the function variant frequencies? No, it's not in any population catalogs. It's in an interesting gene which has a high probability in this new exact gene constraints of being functional because it's really rarely damaged. And so let's go look for this SMAD4 gene in our clinical warehouse. So again, we can go to our clinical exomes and we can search for, again, we could do things like search for rare variants, and this is a project that has just 500,000 variants for 12 samples. Let's go straight to the gene search and look for any variants in SMAD4. So are there any variants in SMAD4? There are no variants in SMAD4 in our clinical exomes. Maybe there would be variants in our research exomes, which is in a different project. So let's go look at this project here. Now we're looking at a scale of 12 million variants over 100 samples. And I can go back into this query interface. And I already had a couple filters set up here. And it remembers your filters from the last time you were in. I was looking for SMAD4 variants that were rare, loss of function. It did found 2. So I can go to this results tab here and find those 2 variants. Now drilling down on this, I get the full details about all these annotations, as well as the full matrix of all 100 of these samples and all of their call sites. So here's a couple of these samples, and I could scroll down and find the ones that have this variant called and see what the supporting allelic counts are, etc. So that's how you can do it from a query interface. And the great thing is with VarSeq, you don't have to come in here and hunt and peck if you don't want to. You can also bulk annotate this data and use it from your own interface, from your own workflow, and it can actually be part of your automatic workflow. So here I'm looking at these 19 de novo samples, and I've actually already annotated these samples. One of the annotation sources is our clinical exomes. So that includes those 17 samples that we had sequenced in our clinical pipeline, and we see that there is no variant information about this variant from SMAD4. If I wanted to add those research exomes, it's as simple as going to add annotation, and here we have our warehouse server as one of our annotation sources. Here's our public annotations, and you can have your own local annotations. But now you can see here's this project that has 100 samples, and I can go ahead and add that. And what this is doing is taking, and I'm sitting here on my desktop versus this data is actually sitting there in the cloud, but it could be on your local server, and grabbing the 50,000 variants here and bulk annotating those against this, the 12 million unique variant sites and their allele counts, and putting that information in a table here. In our research exomes, I had a breakdown against affected and unaffected, so you can see, again, the SMAD4 variant is novel, but some of the other variants in my list here are not. And you can see their frequency and their number of heterozygous counts and homozygous counts, etc. One of these could be used to help tune your filters. One last way you can use this data is from visualization perspective. So if I wanted to understand what's going on with SMAD4, I can open up our Genome Browse tab, and this is something very powerful differentiator of VarSeq that you're not going to see in many other genomic interpretation contexts, is I can look at this mutation here. It's in my daughter that I'm analyzing here, not my daughter, and where it is in SMAD4 and see where it is on this exon. And then these two tracks here are actually the visual representation of those two warehouse catalogs, and any mutations in those catalogs show up in these tracks. So you immediately see in genomic context, there is a mutation in our research exomes nearby. If I click on that, I get the details, I get the allele counts, and you can be able to jump go investigate that sample, and you're doing all this right in the same context where you can see the read level evidence from your BAM files. This is a de novo mutation that looks like really strong support. It's in the child, but it's not in the mother and the father. All right, and so all of that then finally wraps up with having this information be part of your report, and as you add this sample or this variant to your report, you're able to specify the SMAD4 variant as being one that you would keep, and rendering that allows you to put that information back into the warehouse and be able to have that rendered version be part of the warehouse. And with that, I'm going to pass it back to Andreas, who will wrap up and talk about a little bit about how we're introducing this product to the market and next other things that you should be aware of.
Okay, Gabe. Well, thank you very much for a great presentation, and congratulations to you and your team for a fantastic engineering feat here. So just as a general comment, so we spent the time to write up some of the concepts we talked about today in a ebook called Genetic Data Warehousing. This will come out next week, I think. It will be on our website, and Shell will send you a quick reminder. We also touch on implementation issues. I think some of the questions that I can see in the question pane already asked about, or how do we implement distributed queries, and how do we handle situations where we have actually multiple of these repositories, as well as so what are the architectural options, as well as what's the overall implementation approach to all of this. So feel free to download this and use it maybe at least as a reference point for investigating those kinds of questions going forward. I would like to spend a little bit of time to orient you where we are with the launch of VarSeq Warehouse at this point. So as Gabe mentioned in his part a few times already, so a lot of the technology components that are going into VSWarehouse have actually been tested and used in other products like the VarSeq suite as well as SVS. We have been in beta since last year, and in fact this morning we just launched a press release that announced VarSeq Warehouse to the public, and you'll find there a very nice quote, a very generous quote of Dr. Van Darboer of the University of Iowa, who is among others, one of the customers who joined us for this beta program. So we're now going out and talk a little bit in a sort of broader world, basically, about this product. There will be an early adopter program that runs approximately through Q1, and I will talk a little bit more about it. And then the commercial available version of VarSeq Warehouse expect to come out in the second half of March. So about the early adopter program and what would we want to accomplish there. So we would like to build with a few clients really a highly referenceable showcase. We are interested in a wide range of use cases beyond what we have right now with Van Darboer and others, and our plan is to basically write up and create case studies that we then can share with the rest of the community. So that's our goal with this program. So why is it for you at this point? Well, the one big reason, and that is there's almost no price tag to that, is that the early adopters, as the beta customers, have the ability to influence our product roadmap. So if this is an area that you're looking into, and quite frankly, every lab will have to deal with this issue in one way or the other, you are in a position to work with us and potentially help us to prioritize key features. And when those features make it into the core product, there are support, and instead of you having to write custom capabilities that you then have to support yourself. So that's a big reason. But also in the way we are structuring the commitment, we want to make it very, very simple and straightforward. So for the ones that join us for this early adopter program, we will give you what you need in terms of licenses for VarSeq, our pipeline capability, VarSeq reports. We give this basically at no cost. We are charging for the VSWarehouse only 50% of the actual price, so it's a very aggressive price point. And you will, for those of you who have looked at this issue and are trying to solve it right now, you won't find a more cost-effective alternative with commercial database providers. We also give you a 50 months license, and that really accounts for the fact that after the commercial launch, we still plan, in particular in the first 3 months, a few rapid releases that will ship additional capabilities. And so we don't want you penalized for not waiting. We want you to feel like you get the benefit to join us early, and you still get additional extra license to account for all of that. Then some might be asking the question, so what happens after that year? Are our prices going up? And if you're worried about this, we're willing to give you those terms for the early adopters for 3 years. Now there is a fine print with this offer. In our case, the fine print is printed in bold letters here, very well readable. So we would like to wrap up this whole conversation and get your commitment by March 15th. And really, because we expect at this point, based on our current project plan and launch plan, that the commercial product will be available probably just a few days later of that date. So that's what it says right now. And the other caveat that I would like to make is that the offer is limited to 3 customers. The rationale behind this is that we expect a lot more discussions and more interactive dialogues, and we want to do this with high quality, and so we only can do this with a limited number of people, and so I think 3 is a good choice here. And please forgive me if I'm not speaking in absolute numbers here. Just real brief, we have lots of people on this call, and we have also a lot of our competitors, which we love. We like that they're around. They collectively we validate this market, but so there are things that we then prefer to talk with you one-on-one. So if you are interested in this, the best way to get hold of us or to ping us is sending us an email to info@goldenhelix.com and just mention that you're interested in this early adopter program, or you go to our website, find the VSWarehouse pages, and then request an evaluation, and then our area directors that are in charge for the various territories have the authorization to speak on behalf of the company and conduct those conversations with you. So with that, I think we have completed the official part, the presentation part, and Cheryl, I would like to hand it back to you.
Thank you, Andreas, and thank you, Gabe, as well. We have a ton of questions with just a few minutes remaining. So I'm going to take maybe 5 or so, and then from there we will reach out to you with answers for your questions. First up, can you talk about system requirements for Warehouse? Does it run on the cloud?
I guess I'll answer that question, and I see a couple questions along the same theme. It can be installed on your local servers. It does not need to be cloud-based. We can provide a hosted version for you, or you can run it on your own servers or on your own cloud VPC or whatever it may be. And we also, it does not need a big distributed cluster. It can run on a single server, and you should be able to scale with modest system requirements to hundreds or thousands of exomes, and certainly on gene panels, it's going to be no problem. On a gene panel or a small exome workflow, I would imagine you want a 4 or 8 core machine and anywhere between like 16 and 32 gigs of memory. Very modest performance questions. One person was actually asking if this is an Oracle database and you need a separate license for the database component. You do not. It's actually all our full stack here. The front-end SQL engine, which is a proper database query system, is actually the Postgres full language there, and then the back-end is our own highly optimized database at back-end, and Postgres has a great way for you to write your own plugins and data model backends while leveraging their high-performance query optimizer.
Thank you, Gabe. Next question. How does the early adopter program work for existing clients?
Yes, I think the question is there about, okay, I'm a client and I have already bought certain licenses, and now this is coming out. How do you, how is it different from someone who is buying this all from scratch? We will look at everything and on a one-off basis. The principal guideline is that if you're an existing client and you, let's say, renewed or bought your licenses in the last 12 months, we will look at essentially at the equity that you have left in your license, and then we will somehow account for that. So we will find for existing clients a very amicable solution to this.
Okay, thank you, Andreas. Can you describe the capabilities of your API to connect with external systems?
Yes, certainly. So within the context of you control the server, you can control access to these APIs, and you can also control permissions down to a project or level. So for example, different people might be able to access your clinical warehouse samples versus your research samples. And you may want to separate those out into different servers, but there's some ability to also control that within the same server. The APIs, again, you have that raw database view that can be, well, it's not a raw view, but you have this SQL view that gives you this nice abstraction of your warehouse as a bunch of tables. You also will have a higher level Python API and REST API for running things like scripts that give you alerts when things change, or you need to be able to pull information across multiple different components of the warehouse and do some actual back-end integration with other systems, et cetera, et cetera.
Thanks, Gabe. Can Warehouse be used to share data with other researchers?
Yeah, and certainly the idea is that when you buy a warehouse license and you're buying that for a number of users, those users are the ones that from within VarSeq can contribute and add data and update data. But you can choose to have essentially the whole system be read-only for any number of people who have that you want to grant access to. So you can grant access to other researchers that can come in and do those types of queries that I did today.
Last question before we wrap up here. What annotation tracks are included in Warehouse?
Yeah. So we spent a lot of time curating these annotation tracks, and so I can understand why the question is being asked. So our plan is to ship VSWarehouse with all the annotation tracks that we're supporting in VarSeq already, so ClinVar and of course OMIM, DBMS, SNP, Cosmic, NHLBI, 6,500 exomes, and many more. So everything that we're supporting with VarSeq as a standard will come with the warehouse as well.
All right, thank you, Andreas. We are going to wrap. I will have the recording and slides up on the website tomorrow, and I'll email them directly to you, so look for those in your inbox. Our next webcast will be coming up March 2nd, so keep your eyes open for the invite there. And thanks again to Andreas and Gabe for an outstanding presentation. And thank you, everyone, for tuning in, and we will see you next time.